Here is Bob. He really likes chocolate chip cookies. He's eaten them all his life. And here comes his friend, Alice. She works in a bakery and suggests he try her new fancy M&M cookie. Bob is hesitant, but in the end, does taste it. He is not sure whether he prefers it to his usual snack. How will he decide whether to change snacks? Let us model this with maths, with a Bernoulli model. Every time Bob eats the two cookies, he can say he preferred the M&M one, in which case we encode his preference as x equals 1. Or he can say he preferred the chocolate chip one, in which case we encode his preference as x equals 0. Since there is slight variability in cookie quality due to uncertainty in the baking process, x is a random variable. We are interested in its average value p. If p is smaller than 1/2, it means Bob, on average, prefers the chocolate chip cookie, and he can continue eating it every day. If p is bigger than 1/2, then Bob, on average, prefers the M&M cookie, and he should switch snacks. Which one is true? We call the first one the null hypothesis, since it is the one true by default, and the other one is the alternative hypothesis. Let us imagine for a moment that both cookies are very, 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 very close. Maybe Bob prefers the chocolate chip cookie, but just barely. It would take him a very, 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 very long time to detect this difference. And, in the end, does it really matter if he cannot really tell which cookie he likes most, since he loves them both quite equally? Bob therefore decides that if the two cookies are close enough together, he won't bother changing snacks. So, he wants to test now whether p is smaller than 1/2 minus a slack delta, or if p is greater than 1/2 plus the slack delta. What would be the easiest case? If Bob finds the M&M cookie always disgusting, and if he always prefers his chocolate chip one, then p equals 0, and he can conclude very easily, even if it greatly offends Alice. Same thing if Alice crafted the perfect M&M cookie and Bob's initial recipe was gross, he can easily conclude. However, if p is very close to 1/2, it is way harder to decide. In fact, if he manages to decide in the equality cases p equals 1/2 minus delta, or p equals 1/2 plus delta, then every other option is easier. So, Bob decides to only look at the test with null hypothesis p equals 1/2 minus delta versus alternative hypothesis 1/2 plus delta. Bob starts his testing spree. He gathers a batch of n cookies for each recipe and compares them 2 by 2. He gets a bunch of values x1 to xn, describing which one of the two cookies he preferred. What will he do with those values? He wants to measure how much he preferred one cookie over the other, or he wants to measure the strength of the evidence for or against the hypothesis. A method for this is to measure how likely it is to observe what he saw assuming he was in the alternative hypothesis, and comparing it to how likely it is to observe what he saw assuming he was in the null hypothesis. It is more likely to enjoy the chocolate chip cookie if we are in the null hypothesis than if we are in the alternative hypothesis after all. Asking which one is bigger than the other is equivalent to asking if the ratio of the two is bigger than 1. We call the ratio of the probabilities the likelihood ratio. Let us write exactly what this likelihood ratio is. The null hypothesis is that p equals 1/2 minus delta. The alternative hypothesis is that p equals 1/2 plus delta. Each separate observation is independent. The previous pair of cookies does not influence the next. That means that the probability of observing a sequence of observations is equal to the product of the probabilities. Since the probability of x equals 0 or x equals 1 only depends on p, well, we can compute this likelihood ratio easily for whatever observations we have. For that, imagine for example that Bob has tasted the cookies thrice, and that he preferred the M&M cookie once, then the chocolate chip one twice in a row. We replace in the likelihood ratio. Remember that x is a Bernoulli variable, so the probability of having 1 is p. In H0, that is 0.4. And the probability of having 0 is 1 minus p. In H0, it is 0.6. So we replace in the equation, and we get our results. Note that this is smaller than 1. We preferred the chocolate chip cookie more often than the other, and we have a small likelihood ratio. Great! Note that, in a product, the order is irrelevant. So, the order of the preferences does not matter at all. Only the number of times we preferred each cookie over the other will have an impact on the likelihood ratio. Earlier, we said we can compare this likelihood ratio to 1, but we don't have to. We can choose any value and take a decision depending on whether the ratio is bigger or smaller than our threshold. If the ratio is bigger, we pick the alternative hypothesis, and Bob switches snacks. If the ratio is smaller, we pick the null hypothesis, and Bob keeps his snack. How can we choose the threshold then? Let us imagine for a moment that we do a lot of separate experiments over multiple batches. We do 21 batches of 12 cookies each, and have a slack of 0.1. The true p that we would want to learn is at 0.3. We have 21 sets of counts of x equals 0 and x equals 1. For each set, we can compute the likelihood ratio and put it in a graph, building a histogram. What if we had even more batches, say 84? We can again do the same and build a histogram. As the number of batches grows and grows, the histogram will start to converge towards an asymptotic histogram, the one with an infinite number of batches. When we decide on a threshold, the batches with the likelihood ratio lower than the threshold will result in a decision towards the null hypothesis, while those above will result in a decision towards the alternative hypothesis. Here, the real p is 0.3, so the correct decision is to pick H0. Every batch above the threshold yielded a wrong answer. By moving the threshold around, we can reduce this proportion of wrong decisions, or make it bigger. The proportion of wrong decisions here is the proportion of false positives. We chose the alternative when we should not have. The proportion of false positives when conducting an infinite number of experiments is the same as the probability of having a false positive when conducting one experiment. We thus want to limit it. There also exists a probability of false negative, which is the probability of not choosing the alternative when we should have. And, while picking a high threshold could make false positives less likely, we make it very challenging to pick the alternative hypothesis, it also makes false negatives more likely. These two quantities are in opposition, and we want to control both of those. On the remainder of this presentation, we will focus on the false positive rate. One way to do this is by increasing the number of cookies per experiment. Watch what happens as we increase it. The histogram of the likelihood ratio concentrates away from the threshold. There are less errors of both kinds that way. It makes sense. It is way easier to conclude which cookie is better if we have compared them 200 times rather than just twice. How do we choose the number of cookies Bob compares so that we optimize the error rates? Why do we even have to choose? Can't we just eat cookies until we're happy with the result of the tests? Let's try it! Bob eats just 9 cookies, and we chose the threshold so that the false positive rate is 0.05, or 5%. Then Bob eats more, and we get another likelihood ratio, with another threshold, such that the false positive rate for 15 cookies is 0.05 again. That means there's a 5% chance of mistake at the first stage and another 5% at the second stage. The total chance of mistake is 10%, those add up. We cannot just naively eat cookies and conduct a separate test at each time step. What can we do? Well, if we want to test the data sequentially, meaning adapt our tests at each new data point, we will have to look into sequential evidence. We want to quantify an amount of evidence against the null hypothesis. We start with neutral evidence, and the amount of evidence is always positive. If we are in the null hypothesis, there is no reason that we will gather any evidence, so it remains around 1. This is an example of what statisticians call an E-value, for evidence value. What does it mean to stay around 1 under the null hypothesis? So, as we said, we start at 1. For the next data point, there is a probability distribution, but on average, it will remain the same. Same for the next data point. It is random, but on average, it will remain the same. This gives us a trajectory that is not supposed to move too violently in one direction or another, since each data point is on average the same as the previous one. That is what mathematicians call a martingale. The expectation of the next data point is the value of the previous one. We can thus update our definition of sequential evidence. We want it to be a martingale. Now that we have this notion of mounting evidence, how do we use it for our tests? Martingales are very fun, but they are not very edible, and Bob wants to find the perfect cookie. We do the same thing as before. We set a threshold, and if the evidence amount is bigger than it, we pick the alternative hypothesis. After all, if we were in the null hypothesis, the evidence shouldn't pile up too much. Otherwise, we can just continue gathering data until we decide to stop. For example, one evidence we can use is the likelihood ratio itself. What changes from our previous tests is the threshold we will use, so that we don't accumulate error probabilities. For that, let's look at some trajectories under the null hypothesis. We call tau the first passage above a threshold lambda, and set tau to be infinity if the martingale never passes above the threshold. We get a bunch of trajectories, up to some time n. Some of them crossed the threshold before time n, others did not. If we take very, very big n going to infinity, what then is the proportion of trajectories for which tau is finite? How often do martingales cross the threshold? Under the null hypothesis, the probability that tau is finite is the probability that there exists a time, n, on which the martingale is bigger than the threshold, which happens to be exactly the probability that there is a false positive at time n, since it would have led us to wrongly pick the alternative hypothesis. At time tau, either tau is finite, in which case by definition of tau we have that the evidence at time tau is bigger than lambda, or tau was in fact infinite, and the evidence was never bigger than lambda. But we still know by definition that it was always bigger than 0. So, on average, the evidence at tau is bigger than lambda times the probability that tau is finite plus 0 times the probability that tau is infinite. We can make the 0 term vanish, leaving us with the expectation of the evidence being bigger than lambda times the probability that tau is finite. As we said before, the probability that tau is finite is exactly the probability that there is a false positive, so we can replace this in the inequality. This probability is therefore less than the expectation of the evidence over lambda. But remember, the evidence is a martingale over the null hypothesis, meaning it always stays around 1. So, the average value of the evidence is 1. And here is our false positive probability depending on lambda. This inequality has a name in statistics. It is called Veil's inequality. This means that we can pick our lambda smartly in a way that controls the false positive probability however we want. So, to have a false positive probability under 5%, we can pick lambda equals 1 over 0.05. Let's try it. Bob will compare the two cookies. He starts with 9 comparisons. He computes his likelihood ratio. Not enough. Let's eat more. There is a new likelihood ratio. Not enough evidence. Let's eat more. Bob can continue this until he goes beyond the threshold or until he gets sick. Whatever his reason for stopping, the false positive rate remains controlled under 5%. So, what have we learned? Whenever we want to conduct any tests, we start by defining sets of distribution for H0, the null hypothesis, and H1, the alternative hypothesis. Then we can find the most confusing instances, the pair that are closest to each other. By reducing the problem to testing between those two instances, we make the problem way simpler. We can then construct a likelihood ratio test, which is simple to compute once we have the data. Then, finally, we use the threshold that fits the false positive rate that is acceptable to us, for example 5%, and we conduct the test. Now you, Alice and Bob, know how to conduct a sequential preference test to find out your preferred meal. Good luck and bon appétit!